Hi everyone, so this video aims to go through 2022 VJC H2 Chem Promo Paper 2, and we are starting with S1A, where we tell you about car engines. We are mixing ethane with air injected to the cylinders of the engine, and the mixture is compressed and ignited. So S1A part 1 asks you to use the ideal gas equation, calculate the total number of moles of gaseous species the cylinder after combustion. So it's very explicitly stated here that you must use PV equals nRT. My P here is 1.23 times 10 to the power of 6 pascals. Volume is 200 cm cube. We need to convert this to meters cube by multiplying by 10 to the power of negative 6. N is what we're trying to calculate. R is 8.31. T is 753. You need to add 273 to convert it to kelvins. So N will be PV over RT, which is 0.0289 moles to 368. Part 2, calculate the change in the number of moles of gaseous species for combustion. So the change in number of moles of gaseous species will just be the final number of moles minus the initial number of moles. So will be this minus this, which will be positive 8.5 times 10 to the power of negative 4 mole. If you use the rounded off version, you'll get positive 9.0 times 10 to the power of negative 4 moles. And since question is asking you for change, a change can be positive change, which is increase, or negative change, which is decrease. So the sign is important here. Next, part 3. Combustion reaction of ethane, the equation is given to you. So using answer in A part 2, calculate the number of moles of ethane in the fuel air mixture. So first, we notice that, okay, when we burn 1 mole of ethane, the reactants, there is 1 mole of ethane and 3.5 moles of oxygen, which is 4.5 moles of reactants in total. My products, there's 2 moles of carbon dioxide and 3 moles of steam. So there's 5 moles of products. So the change in number of moles of gas particles is 5 minus 4.5 is plus 0.5 mole. So when we burn 1 mole of ethane, the change is plus 0.5 mole, which means that from A part 2, our increase was positive 8.5 times 10 to the power of negative 4 moles. So to produce this increase, the amount of ethane needed would just be this divided by 0.5 would be 1.7 times 10 to the power of negative 3 mole. Part B, this time we are burning pentane, and we note that the energy delivered by the test engine is this in this unit per hour. So to calculate the amount of energy would just be this multiplied by 2 since we are looking for 2 hours. So the energy delivered will be 5.6 times 10 to the power of 4 kilojoules. Part 2. Calculate the volume of pentane required to deliver the energy in B part 1. So this is the enthalpy change of combustion of pentane. So this is negative 3510 kilojoules per mole. But from B part 1, I want to release this amount of energy. So the amount of pentane that I need will be this number divided by 3510. I will need 15.954 moles of pentane. So given this, I can find the mass of pentane by multiplying this by the MR of pentane. So I will need this mass of pentane. And finally, the volume of pentane needed will be the mass divided by the density of pentane, which will give me this number 1834.9 cm cube. If I round off to 368, it will be 1830 cm3. Okay, C, the fuel energy value in kilojoules per gram is the heat energy released when 1 gram of the substance is burnt. So it is a bit similar to enthalpy change of combustion, except that this is per gram of substance, whereas enthalpy change of combustion is per mole of substance. So it's a bit different. So in this case, we are trying to investigate liquid ethanol. So part 1, write equation for the standard enthalpy change of combustion of liquid ethanol. So quite easy to write. Please remember to include your state symbols. Next, part 2, using the data provided, calculate the mass of ethanol left in the canister. Now, this question obviously requires you to use Q equals mc delta theta, and you'll notice that the m is usually the mass of water that we have used in the reaction. But in this case, we have given you the heat capacity of the calorimeter, and this is a hint to you that you need to use it in your calculations because the calorimeter also absorbs heat of its own. Okay, so in this case, we need to modify that equation a bit. So the total energy that is evolved it comes from two parts. One part is the heat that is absorbed by the water, and another part is the heat absorbed by the calorimeter. So the heat absorbed by the water will just be mc delta theta. Mass of water 200 grams. Heat capacity of water 4.18. The temperature change or temperature increase is 24 degrees Celsius. And the heat absorbed by the calorimeter is just its heat capacity multiplied by temperature change, so 19.3 plus times 24. So the total amount of energy released is 20,500 joules. So since we have found that the energy released is 20,500 joules, and we are given the value early in the question which states that burning 1 gram of ethanol releases 23.3 joules of energy, 23.3 kilojoules of energy. So we need to convert 23.3 kilojoules into joules first. So the mass of ethanol will be 20,500 divided by this number. So the mass of ethanol left over in the container was this mass, 2368. Part D, we have a compound called tetracarbonyl nickel. Values of delta H and delta S are given to you. D part 1, explain the significance of the sign of delta S negative, or the delta S standard, the standard entropy change. So now we know that entropy change measures the amount of disorderliness in the system. If you have a positive value of delta S naught, it means that entropy change is positive, system has become more disorderly. And the opposite is also true if my value of delta S naught has a negative sign. It means that my system has become more orderly. So for this question, the demand on you is to explain with reference to this equation, why does this delta S not have this sign of which is a negative sign. So you notice that my reactants has 4 moles of gas, but my products have only 1 mole of gas. So there is a reduction in the amount of gas from reactants to products. So you need to tell me that the entropy change has a negative value. So the significance of this is that the system has become less disordered or more ordered because there is a decrease in the number or the amount of gaseous particles in the system from 4 moles to 1 mole, which results in fewer ways to arrange the particles, and so the entropy of the system will decrease. That's why it explains the negative sign of delta S. Part 2, we are required to sketch a graph of delta G against T. So this should be a hint to you that you need to write down your equation first. So delta G equals delta H minus delta S. Okay, so we will rewrite this so that we can plot delta G against T. And this will resemble your straight line equation y equals mx plus c, which means that a graph of delta G against T, the gradient is negative delta S. In this case, my delta S is negative. So negative of this becomes positive, which means that the graph we're plotting has a positive gradient. And this is C. C is my y-intercept. In this case, it coincides with my standard enthalpy change. So this is how the graph looks like. You are required to show a positive gradient and to label the y-intercept as negative 161 kilojoules per mole. Next, we're moving on to question S2A part 1 to outline the mechanism of reaction between methane and bromine. So this is free radical substitution. A similar question has actually appeared in 2023 promos as well. So nothing much new that I want to re-emphasize. So basically the only thing to remember is the use of half arrows to show how the Br-Br bond undergoes homolytic fission in the initiation step. Part 2, how come we can use light of a longer wavelength to do bromination, whereas we can only use a shorter wavelength light to do chlorination? So it's really mentioned here that the longer the wavelength of light, the less energy it has. So if we can use a longer wavelength to brominate methane, what it tells us is that the bromine-bromine bond will be weaker than the chlorine-chlorine bond. So you will need to explain why the chlorine-chlorine bond is stronger than the bromine-bromine bond. And this is due to the difference in size of atoms for bromine and chlorine. So because bromine atoms are bigger than chlorine atoms, when the orbitals in bromine atoms overlap to form bonds, the overlap is less effective, which results in a weaker covalent bond being formed than between chlorine atoms. So we can break a bromine-bromine covalent bond much more easily than a chlorine-chlorine covalent bond. Part B, in chlorination, the rates of removing the first H atom from ethane and methane are 270 to 1, which suggests that the first hydrogen atom is much easier to remove from ethane than methane. So why is this the case? So you need to look at the type of radical that is formed after you remove the H atom from both methane and ethane respectively. So if you remove a H atom from methane, it becomes a methyl radical. But if you remove a H atom from ethane, it forms a primary radical. And the primary radical, there is more alkyl groups attached to the carbon which bears the unpaired electron. And this alkyl group, it exerts what we call the electron donating inductive effect. And it increases the electron density on the radical carbon. So the equations are there. So because the primary radical formed from ethane is much stabler than the methyl radical formed from methane, it makes it easier to remove the first H atom from ethane compared to methane. When propane reacts with chlorine in the presence of light, it forms 3 isomers with C6H14 formula with different boiling points. Okay, so first you're going to look at the structure of propane, and you're going to notice that there are 2 places where H can be removed to generate a radical. So if you remove one of the blue H's, it generates the radical as shown now. If you remove any of the red H's, it generates another radical. So we are going to call this radical A and radical B. So how do the 3 isomeric products come about? So you can have 3 cases where radical A collides with another radical A collides with radical B, or radical B collides with another radical B. So if you have 2 times radical A colliding, you will end up with this structure, and that is the skeletal formula. If you have 2 radical B colliding, you will end up with a straight chain isomer, and that is the skeletal formula. If you have radical A colliding with radical B, this is the structure, and this is the skeletal structure. Next slide, Q has higher boiling point than the other 2 isomers. So Q will be the straight chain isomer. So explain why Q has a higher boiling point than the other 2 isomers. So this is testing you on the effect of branching of hydrocarbons on boiling point. And we know that the lower the degree of branching in the hydrocarbon, the lower the boiling point. So first you must mention that Q is a straight chain isomer of hexane. The other 2 isomers have certain degrees of branching. And when the molecule is straight chained, there is a larger surface area of interaction between the molecules, which leads to stronger ID-ID interactions and require more energy to overcome to boil Q compared to the branch chain isomers. Part D, methyl cyclohexane reacts with bromine to form a dibrominated product R. So compound R exists as a mixture of stereoisomers to draw the structure of each stereoisomer. So first thing in R, we note that the type of stereoisomers present is optical isomerism, because you notice that there are 2 chiral centers in the molecule, so which will lead to 4 stereoisomers, 2 to the power of 2. So the easiest way to do this is to fix the Br with one type of bond first, and to vary the methyl and the Br on the other adjacent carbon. So for example, by this tool, I fix the Br using a wedge bond, and then the adjacent carbon with the methyl and bromine, I vary the bonds for both methyl and bromine. So this one is bromine with hash, methyl with wedge, and this one is methyl with hash, bromine with wedge. And then I do the same, except that this time I've used the wedge for the Br. So now I'm going to use the hash for the Br, and I do the same by varying the bonds. So these are the 4 stereoisomers for R. Next, we're moving on to question E1, where we have given you 2 dissociation equilibria for weak diprotic acid, which is carbonic acid. And A part 1 requires you to calculate the concentration of carbonic acid in 25.0 cm³ of seawater, with the assumption that the second dissociation step of carbonic acid is negligible. So first, we will need to start with the Ka expression of the first dissociation. So using this, our Ka expression can be written like this. And since our dissociation of carbonic acid produces the same amount of H plus and HCO3 minus ions, we can rewrite this expression as concentration of H plus squared over the concentration of carbonic acid. Now, with this, we can substitute in the figures that the question has given to us. So, since the pKa1 for this dissociation is 6.37, so Ka will be 10 to the power of negative 6.37. And since the pH of seawater is 3.68, it means that my concentration of H plus is 10 to the power of negative 3.68. So we can substitute this into the Ka expression, and you will find that the concentration of carbonic acid will be 0.102 moles per dm cube, 368. So part 2 and 3 for question E1A is not tested for promos. So we're going to skip directly to B part 1, okay, which is to define the term buffer. So this is just a basic recall question. Your answer must have two parts, which is that firstly, buffers can maintain a fairly constant pH. Second point is that only when small amounts of acids or bases are added. Okay, B part 2 is not tested for promos as well. So we move on directly to part 3, where we want to use the ratio given in B part 2 as well as these equations to calculate the concentrations of both ions in the lake. So from part 2, this is the ratio of both ions that they have given to us. So we are going to define the concentration of hydrogen carbonate ions as Y moles per dm cube. So the concentration of carbonate ions will just be 0.958 of Y mole per dm cube. Then we're going to calculate the amount of both ions in the lake water. So the amount of hydrogen carbonate ions will be concentration times volume. Volume is 25 cm cube. So the amount of hydrogen carbonate ions is 0.025 Y moles. And comparing this with the stoichiometry of this equation, we will need the same amount of hydrogen ions to react with this amount of hydrogen carbonate ions. Secondly, our concentration of carbonate ions is 0.958 Y mole per dm cube. So the amount again will be volume multiplied by concentration, which is this amount of carbonate ions. And this amount of carbonate ions reacts with hydrogen ions in a 1:2 stoichiometry. So the amount of hydrogen ions needed, 0.0479 Y mole. So what it means overall is that to react with both ions present in lake water, the amount of hydrogen ions needed will just be the sum of these two, which is 0.0729 Y moles. And this is the same as the amount of H plus ions that is present in 22 cm cube of 0.2 mole per dm cube of HCl. So we equate these two and we solve for Y. Y will be 0.0604 mole per dm cube, which is our hydrogen carbonate ion concentration. And 0.958Y will be 0.0579 mole per dm cube. And this is the concentration of carbonate ions. Both of these numbers were given to 366. Okay, next part. Part C, we have an equilibrium reaction between carbon monoxide and nitrogen dioxide. The first thing that we can tell from the reaction is that they react in a 1:1 stoichiometry, which means that at any point in the equilibrium reaction, the concentration of both of these gaseous species will always be the same because they will be decreasing at the same rate. So next part 2 is to complete table 1.1. So how do we do so? Okay, so the concentration of carbon dioxide at each time is given to us. So what we can do, since looking at this reversible equation, all of your gaseous species are in a all in a 1:1 stoichiometry. We need to notice that any increase in the concentration of carbon dioxide is the same as my decrease in concentration of both CO and NO2. So from T equals to 0 seconds to T equals 5 seconds, my carbon dioxide concentration has increased by 0.5 mole per dm cube. So my concentration of both my reactants has decreased by the same amount to give me both 0.500 mole per dm cube. Then for this column, I'm just going to multiply these two concentrations at the particular time. So will give me 0.250 mole square dm to the power of -6. Then I repeat the same. So again, over here, there is an increase of 0.190. So here will decrease by 0.190 for both, so on and so forth. Then we move on to this column. So sample calculation is given to you, where it is the change of concentration of carbon dioxide compared with the change in time. So for example, over here, at time equals to 10 seconds, okay, my concentration of carbon dioxide is 0.690 mole per dm cube. So comparing that to 5 seconds, my change is 0.190, and the time that has passed is 5 seconds. So I'll press calculator and you'll get 0.038, and the same for 15 and 20 seconds. Part 3, using the table in 1.1 to plot a suitable graph to determine or to confirm that the reaction is overall second order kinetics. Now, if you have read the question properly, okay, overall second order can have 3 cases in this with reference to this reaction in general. If the question didn't state, then overall second order can be second order with respect to CO, second order with respect to NO2, or first order with respect to both reactants. Then the overall order of reaction is the sum of both orders, which is 2. And this is the one that is mentioned in the question. So what we're going to do, we are going to plot the rate of the reaction against this. And if this is the correct rate law, what we should get is a straight line with the gradient being the rate constant K. So this is how your graph looks like, and you can see that it follows a very nice linear graph which passes through the origin. So we've already mentioned that the value of the rate constant is the gradient of the graph. So you just find your 2 points on the graph to calculate gradient as 0.400 with the correct units of mole to the power of -1 dm cubed per second. Next, if R is the rate of reaction between CO and NO2, what happens to the rate when both CO and NO2 partial pressures are doubled? So we've already established that the reaction is first order with respect to both gases. So we are going to do it step by step, okay? So when I double the NO2 partial pressure, CO partial pressure remains constant, my rate will double because it is first order with respect to NO2. Then from there, I double the concentration of CO. My rate is going to double again to give me 4 times the original rate. So by doubling both partial pressures, my rate will multiply by 4 times, which means that my new rate will be 4R. Finally, we are moving on to question E2. where we have given you the structure of a compound called beta ionone. So part 1 state the hybridization for carbons 1 and carbon 3. So to identify the hybridization for carbon in an organic compound, we're just going to look at the number of bond pairs around the carbon atoms. So C1, you notice there are 3 bond pairs around C1, which suggests that it is sp2 hybridization. Whereas for C3, okay, there are 4 bond pairs around it, which suggests that it is sp3 hybridization. Next, to draw labeled diagrams to show how orbitals overlap between C1 and C2. So first thing, okay, between C1 and C2 is a CC double bond, which means that there are actually 2 types of bonds. There is a sigma bond formed by sp2, sp2 overlap from both carbon atoms, and then the unhybridized p orbitals from each carbon atom are going to overlap to form a pi bond. So what do we expect from a diagram? Your diagram should look like this, okay? So you need to show the sp2 orbitals from each carbon doing a head-on overlap in forming the sigma bond, as well as the unhybridized p orbitals. They overlap side-on to form the pi bond. Part B, beta ionone has 2 CC bonds. State and explain the possibility of cis-trans isomerism for each CC bond. So the 2 CC bonds are here and here. So we need to find out whether each CC bond can exhibit cis-trans or not. So for this one, okay, for skeletal structures, the H's are not shown, but there is one H here and there is another H here. So for this double bond, okay, there are 2 different groups attached to each carbon atom in the double bond, and the CC double bond is rigid, so there is restricted rotation around the CC double bond. Okay, so therefore this CC double bond is capable of exhibiting cis-trans isomerism. Next, we look at the CC double bond in the ring. So for alkenes or CC double bonds in rings, cis-trans is generally not possible until or unless you hit a certain ring size. And why? Because for this double bond to exhibit cis-trans, the ring will have to twist in a way that causes significant ring strain. So the key phrase here is ring strain. Due to the phenomenon of ring strain, it makes this double bond unable to exhibit cis-trans isomerism. Part C, when beta ionone undergoes electrophilic addition with HBr, it forms A. So draw the mechanism, show the relevant charges, dipoles, lone pairs, and curly arrows. So even if question did not give you the name, or even if question did not prompt you, the first thing you should write is the name of the mechanism. So second thing to take note is the arrows, okay? For free radical substitution, our initiation step is shown using half arrows, which shows the movement of 1 electron. For any other mechanism, you need to show using full arrows. So the arrow originates from a region of electron density. In this case would be the CC double bond, and the arrow head is at a region that is electron poor. In this case, it will be the H atom, which bears a partial positive charge in the HBr molecule. So this is the first step. It is the slow step which leads to the formation of carbocation. So the next step is the fast step, okay? The Br minus is a nucleophile. It contains a lone pair, which it uses to attack the carbocation intermediate and form the product A. Part 2, okay, compound B is a minor product. and the intermediate of this reaction. So we know that for electrophilic addition reactions, intermediate is a carbocation ion. So you just need to draw the carbocation ion intermediate, which led to the formation of B, which looks like this. Okay, so, and then the Br minus is going to attack this C plus to produce the product B. So by considering the relative stabilities of the intermediates form, explain why compound B is a minor product. So you are needed, what is required of you is to consider the stabilities of both carbocation ions. Since compound B is minor product, it means that this carbocation ion is more difficult to form. So your answer must explain why it is more difficult to form this carbocation ion compared to this carbocation ion. So there are two factors that you can use to explain. Any one factor will do. So first thing, we notice that this intermediate for A is a tertiary carbocation ion. There are 3 alkyl groups bonded to the atom which carries a positive charge, whereas this intermediate is a secondary carbocation ion. So tertiary carbocation ion is more stable than secondary carbocation ion because there are more alkyl groups bonded to the C+, and alkyl groups exert the electron donating with inductive effect. So the more alkyl groups there are attached to the C+, the more the dispersion of the positive charge on the carbon atom, and this increases the stability of the carbocation ion such that it favors the formation of this intermediate. So that is the first factor. You talk about stability of carbocation ions in terms of the electron donating inductive effect. Second one, you notice that for this intermediate for B, it is very close by to a carbonyl group, or more specifically a ketone. And this ketone is actually electron withdrawing. So opposite to the alkyl groups, this ketone group actually exerts what we call the electron withdrawing inductive effect. And when this C plus is very close to the ketone, it will intensify the positive charge on C plus, and this destabilizes the carbocation ion for B, and it makes it harder to form. So either one of these explanations will be used to explain why A is more favored than B, which leads to B being a minor product. Okay, lastly, part D, we have a reaction scheme. Okay, so from C to D, we have C is C13H17OH, becoming D is C13H16. So it is an elimination of water from alcohol to form alkene. So it's either excess concentrated sulfuric acid with heat or aluminum oxide with heat. Next, part 2, we know that D is an alkene. When D is heated with hot acidified KMNO4, it produces a mixture of products. So this is actually the oxidative cleavage of alkene. Okay, part 3, deduce the structures of C and D. So this one is very similar to one of the tutorial questions, where you have to piece back the original structure of the alkene based on the products. So we know that D is an alkene, and after oxidative cleavage, it forms CO2 and H2O. And this tells us that a CH2 group is present in the original alkene. Next, we also notice that this diketone is present. So the original fragment that led to this diketone, it will look like this. And lastly, it forms a benzoic acid. So, which means that this structural feature is present in alkene D. So we just have to put these three groups together. So which tells us that the structure of alkene D will look like this. So there are possible structures of C. There are two possible structures of C, in fact. So we know that C is an alcohol. After we eliminate water from the alcohol, it forms D as the only product. Keyword here, only product. So you can put the OH either onto this terminal carbon or onto this carbon, such that there is only one place where the double bonds can be formed for D. If you put the OH here or here, it can eliminate in multiple places to give a mixture of products. So for example, this one can eliminate like that to form a double bond here or to form a double bond here. Same for this, it forms a double bond here or a double bond here or double bond here. Yeah. Okay. Lastly, we have ethanol manufactured by reacting ethene with steam. So first part, to write the Kc expression for the reaction. Now, many students will fall into the trap. They think that the moment you see H2O, you don't need to write it. But this is not an aqueous equilibrium. It's actually a gaseous equilibrium. So which means that you will need to consider your H2O gas in your Kc expression. So this is the Kc expression. And then, okay, a mixture containing these amounts of ethene until equilibrium, and it was reached when 5% of ethene had reacted, volume of the vessel 2 dm3. So we're going to set up our ice table. So our initial concentrations of ethene is 2/2, which will be 1 mole per dm3. Our initial concentration of steam is 1/2 mole per dm3, or 0.5 mole per dm3. Initially, there was no ethanol present in the system, but after equilibrium, I had formed 0.05, the change of concentration of ethene is minus 0.05 times 1, because 5% of the ethene had reacted. So this represents that 5% of the ethene had reacted. The concentration of ethene had decreased by 5%. So the change in concentration of ethene is minus 0.05, and that will be the same change in concentration for steam. So these are the equilibrium concentrations of ethene and steam. The final change in concentration of ethanol will be plus of this, because all of them reacted in a 1:1:1 stoichiometry. So the equilibrium concentration of ethanol is 0.05, and then I'll just substitute it into my Kc expression. So Kc will be 0.05 divided by 0.95 times 0.45 would be 0.117. Finally, explain how a decrease in temperature changes the yield of ethanol. So this question obviously is testing you on Le Chatelier's principle. So Le Chatelier's principle predicts that when I decrease the temperature of my reversible reaction, the equilibrium is going to shift in a way that favors exothermic reactions, because exothermic reactions release heat to counteract the decrease in temperature. So we note that the forward reaction here is exothermic. My POE will shift right. Sorry, there's a typo here. The POE is going to shift right, and this results in an increased yield of ethanol. So with that, I've come to the end of this video. Thank you.